Okay, this lecture is on the Cantor set. It's a very important set. I will confess it's an act of joy for me. I have a long-running love affair with the Cantor set. Let's talk about it. We're going to construct it. We're going to do it in stages. We're going to start out, and by notation, we'll let C sub 0 be the closed unit interval. And then C1 will be obtained from C0 by removing an open third. So this, you can see this down in the picture over here on the left. I've constructed C1 from C0 by removing the middle third of it. Okay. I want you to notice that C1, whereas C0 was one closed interval, C1 consists of two closed intervals, and that each of which is a length that is 1/3 as much as C0. Okay. And so say we've constructed some intervals by a process so that Cn consists of 2 to the nth disjoint closed intervals, each of which is of length 1/3 to the nth power. We may create now Cn plus 1 from Cn by removing the middle third of each of its disjoint closed subintervals, just as we did for C0. This will leave 2 to the n plus 1 disjoint closed intervals, each of which is of length 1/3 to the nth power. Okay. So let Cn be the set of all the points that these Cn have in common. We will call C the Cantor set, or the Cantor middle third set. Okay. All right. I want to figure some properties of this. Let's see. We'll show that first it's of measure 0. Okay. Let U sub 0 be the open interval from -1/10 to 11/10. So we've just fattened up our closed interval C0 by a little bit, and we've chosen so that UN is 6/5 of length. Okay. Now we multiply this set U sub 0 by 1/3 to get an interval we'll call U11, and then we'll say, okay, let U12 be equal to U11 plus 2/3. So we're using some of our algebraic properties, or the properties of the real numbers, to move these pieces around and save us notation. Then we see that U11 and U12 covers the set C1, and since it covers C1, it's going to cover the set C as well. And the sum of the lengths of these intervals is 2/3 times 6/5. We can continue this way, constructing a set of open intervals UIN, where I equals 1 to 2n, that covers C and has a total length of 2/3 to the nth power times 6/5. Okay. Now let epsilon greater than 0 be given. Choose n so that 2/3 to the capital N of 6/5 is less than epsilon. Therefore, U to the 1 in that set of open intervals covers C. It has a total length less than epsilon. Therefore, C is of measure 0. Okay, so the measure 0 thing is taken care of. Now, so maybe it's not a surprise that this is measure 0 because we saw it getting smaller. The surprise may be that it contains anything at all. First off, note that the point 0 is retained at every stage in the construction, so C is not empty. Okay. What might be more surprising is that it is in fact uncountable. Okay. First, let's start off with I sub 1 to be the closed. Okay. Well, suppose we do have a function from the natural numbers to C. Let I sub 1 be the closed interval component of C sub 1 that does not contain phi of 1. Okay. They'll have to be 1 because we have two components. Phi of 1 has to be in one or the other. Let I be the one it's not in. Now, suppose that we have constructed all of these intervals down the line. So that my I sub k is a closed interval component of C sub k that does not contain phi of k. Now, if we take the intersection of I sub n with Cn plus 1, that contains two intervals. Okay. At most, one of those can contain our phi of n plus 1. Let I sub n plus 1 be one of the intervals that doesn't contain phi of n plus 1. Okay. So there is a unique point that's common to all of these phi of I. That's the unique point C contained to all of them. And this C is not equal to phi of n because phi of n is not in I sub n. Therefore, the Cantor set is uncountable because we can't map the natural numbers onto it. Okay.